So we ended up, the last chapter talking about DC coupled amplifier circuits, and we were talking about terminal characteristics of these amplifiers. One type of amplifier that we will use as a block, we will not, build from a transistor level, is the op amp, right? So in general, amplifiers can be built, and the op amp is actually constructed from a transistor circuit. So inside the op amp, which we will use in this chapter merely as a block, there are lots of transistors inside, resistors, capacitors, etc., etc. So we will not be dealing with that, with the op amps details in this class. This is like chapter 12 material. This is, I think we offer that in 326, for example. The next level after this, the 325 course. So here we will use the op amp as a block and build circuits around it. And we will justify why we will build circuits around it, hopefully today. Okay, so as we said, it's a kind of amplifier. It will be mainly utilized as a voltage amplifier or a buffer. So we'll either utilize it as a voltage amplifier or a buffer. Yeah. So as we said, it's constructed of, lots of transistors inside. So inside it, there are lots of transistors and resistors. Again, like anything, it started as an expensive piece of, expensive device that costs, tens of dollars, for example, versus today it's, cheap, tens of cents, or even less, right? So you can buy very cheap op amps today and utilize them. Yeah. Yes, ma'am.
In 2014, we studied something called a realistic op amp.
The ideal op amp.
No, not the ideal. Like realistic. Are we gonna study only ideal or?
No. We will start with ideal, but we will move to realistic op amps.
Oh.
So you studied op amps in 214, right?
Yeah, but only ideal ones. Like we didn't. It's just this is the formula for the inverting. This is the formula for the non-inverting.
Okay, so that's good. So we'll start that today. So just the formula. You did not derive the formula.
No, she derived the formula, but we didn't have to derive it ourselves.
Okay. In our case, we will have to be able to derive that because it's going to depend. It will, yeah. And your understanding will be improved if you start deriving these formulas. So I think we will go and derive these formulas in the class. But yeah, the beginning of it is very similar to 14 then. The inverting, non-inverting, but we will start talking about the non-ideal characteristics. So the ideal op amp has a gain of what? The ideal. If you study 214, what is the gain of an ideal op amp? Open loop gain of an ideal op amp? No? Infinite. You remember? No?
I don't know.
Okay, so anyway, we'll study this. We'll study this in this chapter. So the symbol for the ideal op amp that we will utilize is this 3 terminal symbol. So we'll use this 3 terminal symbol for the ideal op amp, and as we discussed before, the ideal op amp has a terminal called what? This is the plus terminal is called what? Non-inverting input, and then this is the inverting input. Why? It's because of the way the output equation is configured, and we see the output equation right now. So it's a minimum of 3 terminals. As we said, the output is going to supply a voltage that is amplified or a current that is amplified versus the input. And where is that coming from? From supplies, external power supplies. These external power supplies can be like a positive and a negative, and this is called a dual rail configuration, or it can be a ground and a positive, single rail configuration, right? So, and the output of the op amp can only be between the supply rails. You cannot have the output be more negative than minus VEE or more positive than VCC, right? Because it will saturate at it will saturate at levels close to these quantities. Yeah. The other point to note is yes, sir. Yeah, this is like the actual circuit. When you come build a circuit, you will put a battery, for example, in this polarity and a battery in this polarity and connect them to 4 and 5. Right? But it's just another representation. There's no ground port.
No, but
so
the voltage is connected, and then the other,
you will take the output voltage between node 3 with respect to ground.
Yeah, but CVE. And VCC?
VCC, VEE,
They're
yes,
all
of
connected
course.
to ground also.
Yeah, this is the circuit ground,
So
right?
we're going to build this, right, physically?
Sure, you
So
will build
when
it.
we connect the VCC, we will connect it on one side and the other is ground.
Yes, but the op-amp chip itself does not typically have a ground connection. Right?
Okay.
Right? So here, this is the op-amp chip. This is the external power supply. You will create an external power supply, and your circuit will have a ground or a common point. Your op-amp your op-amp chip itself will not have a ground potential. It will have two supply terminals, and one of these supply terminals, if you are utilizing it as a single rail op-amp, then will be the ground, but not necessarily, right? So in the general case, you have two supply terminals there. As we said, inside this is lots of transistor circuits, right? So inside this is a lot of transistor circuits. The other, special terminals that we will look at later in the chapter are, frequency compensation terminals and offset nulling terminals. What does this mean? So remember, we said that the op-amp is an amplifier, and the amplifier, what's the bandwidth of an ideal amplifier from last chapter? What is the bandwidth of an ideal amplifier? Bandwidth of an ideal amplifier.
Remember simplicity.
It's the last thing we talked about. What's the bandwidth of an ideal amplifier? Ideal meaning what? It's not affected by frequency, for example, right? So what is the bandwidth of an ideal amplifier? It's infinite. It can take a signal of any frequency, and it can produce an output of any frequency, of any frequency, right? So that's the ideal amplifier, right? And it's the same thing with an ideal op-amp, right? So of course, a real op-amp is not that way, right? A real op-amp will have a limit with respect to frequency. Why? Because it's a physical device. Any physical device you build will have resistors, capacitors that will create lossy components, will create losses due to resistors, and will create frequency dependence due to the capacitance that you have, even if it's a parasitic capacitance, not the capacitance that you've designed and built in there. Just having two nodes next to each other with different potential is a capacitance, right? So even parasitic capacitances will cause an op-amp to be affected with frequency. So at some point, even if it's so far away, right? If it's a very, very high frequency, then it's still affected by frequency. So sometimes you need to do some frequency compensation. So sometimes some op-amp chips will have frequency compensation inputs. Something else, sometimes you have an input called offset nulling. So sometimes the signal will have the measured physical phenomena, and as well maybe some shift due to, for example, your circuit itself caused the fixed voltage to be applied to one of the op-amp terminals somehow, by electromagnetic interference, by capacitance, whatever it is. You want to sometimes null that offset. So this will eventually be passed through the amplifier. If we looked at our transfer characteristics for the op-amp simple amplifier model that we used last time, anything coming in will actually go out, maybe amplified as well, right? So sometimes you don't. If there's an offset that you have at the input, you want to be able to null that, make it zero, maybe. So that's another input that sometimes you will see in a real op-amp chip, and we will talk about that towards the end of the chapter. Yeah. But minimum, you have 3 terminals and 2 power supply terminals. So some chips you buy an IC semiconductor with, for example, 4 op-amps inside it. This chip will have what? 3 legs for each op-amp, and then a power supply terminal plus and minus for the whole chip, right? So what does so this is here. So for example, this exercise, what is the minimum number of terminals required for a single op-amp? 5, right? So 2 inputs, 1 output, and 2 supplies. That's 5. And then if you have, what is the minimum number of terminals required for an integrated circuit package of 4 op-amps? So 4 times 3 is 12. 12 and 2 supply terminals is your 14. Right? So what does the output of the op-amp look like? So the op-amp model is yes, ma'am. What is 14? Why? We have the op-amp will have minimum 3 terminals and then 2 power supplies. So the chip will have 4 op-amps, so it will have minimum of 3 per op-amp, so 3 times 4 is 12. And then there's a power supply rail that's common to the whole substrate. So they were talking about how many legs that the chip will have, for example, right? Minimum. So okay, so now let's see. So we have plus here, minus here. This we will call, V1. This we will call, sorry. This we will call V2, and this we will call V1. Okay, and then this will be my output here. The output is with respect to my circuit reference. Okay, so this is my V output. It's always going to be with respect to your circuit reference. Okay, and your input.
What does that mean?
You have to measure with respect to a reference, right? So your output will be with respect to your reference, which is ground in this case, right? So okay. So what will this what does the op amp do? The op amp output is equal to A V2 times V1. So A V2 minus V1 is the op amp output, right? So the minus or V1 is called the inverting input because you're taking that voltage and multiplying by a minus sign and then amplifying it at the output, versus the non-inverting input is you're multiplying the gain by the voltage itself. No, all of this is the general op amp output equation, the op amp itself. Then we will see what we will do with the op amp. Yeah. So, and this A is ideally infinite. A is ideally infinite. If A is infinite, right, is the output a defined quantity? So this is AV2 minus V1 is equal to V output. If A, I'm saying, is infinite, is the output a defined quantity? It's not a defined quantity. You don't know what it is, right? You do not know what the output is, right? Which is why we have circuits to add around the op amp before using it, right? So the op amp as it is not very useful unless you're doing a comparator, unless you're building a comparator. If all you're doing is comparing V1 and V2, let's say you're putting V2 is equal to 3 volts, V1 is equal to 1 volt. What is the output going to equal? 3 minus 1 is 2. 2 times infinity is a large positive number, right? A large positive number. Is the output ever going to go in a real op amp? Is the output ever going to go beyond the positive power supply rail?
No.
It will not go beyond the positive power supply rail. So what will the output of this device look like if my power supply is plus minus 5 volts?
It's going to be plus 5 volts.
It's going to be plus 5 volts, exactly. And if I flip these, I put 3 here, I put 3 here, and I put 1 here, then the output is A minus A times negative 2, right? 1 minus 3 is negative 2. So the output will be infinity times negative 2, so it's negative infinity, right? So the output will saturate to negative 5 in this case. So this is 5, this will be negative 5, right? So it's great if I want to operate as a comparator.
Do you want strictly?
This is called slew rate. We will talk about it later. No, everything takes time. So we will talk about that. Yeah. So this is not useful unless you're using it as a comparator, right? But we were not talking about comparators. We're talking about amplifiers, right? Amplifying a signal, amplifying current, amplifying voltage. So if that's the case, then I really don't want to use the op amp as it is. I would like to be able to figure out a way to make it useful. I mean, I don't want to just keep saturating my outputs here to a supply rail or negative supply rail. I want to have a signal at the input and amplify it by multiplied by 2, multiplied by 2.5, or multiplied by 3, right? You want to be able to take this signal and put it into an ADC afterwards. Analog digital converters, their input will be 0 to 3 volts, for example. You cannot just put an infinite, saturate it to the supply rail and that's it, yeah. So what do? You build circuits around it, yeah. Other characteristics of the op amp. So here, ideal op amp is supposed to be, so the gain. No, this is not the gain. They're talking here about the input impedance. Yeah. So another consideration. The ideal op amp, like we were talking about in the last chapter, I would like to have input of the op amp. This was our input. Remember our input? We had our sensor, the last chapter we had, we had a sensor and we had the R sensor, and then we wanted to connect this to an amplifier. And we said that I would like, ideally, the R input of the op-amp to be what? I would like to take, this is my V sensor, I would like V input here to approximately equal V sensor. For me to do that, I want what? I want R input
To be much bigger.
to be ideally infinite. If R input is ideally infinite, then I'm not drawing current. If I do not draw current and there's no voltage drop across this resistor, then Vs is equal to V input, ideally. Right? So the ideal op-amp behaves exactly like that. Right? Why? How does it do that internally? Again, we will not study the internal circuit, but we will have to. If we say that it behaves like similar to an ideal op-amp, it means that by itself, like this, current will not. If you connect the signal, current will not flow. So I here will be 0, and I here will be 0. Right? There will be no current flowing in. It's like, the terminals will come in and then they will be terminated. Here, this is my op-amp. It's an open circuit. Right? That's the ideal op-amp. Right? So no current will come in. So the I equals 0. Ideally. Right? This is only for the ideal op-amp. Yeah. So this is nice. This is excellent. I mean, we like this characteristic because it's not going to load my sensors and it will only measure the voltage that the sensor is producing. Correct? So that's a nice characteristic, but of course I don't like the idea of, so even though I will be measuring V input, as soon as I have V input, what's going to happen? It will be multiplied by the gain, which is infinite, and go to the output, which means it will saturate. So what does this mean for V2 minus V1 that is going to be useful? If I'm gonna have V2 minus V1, if I'm going to have some sort of output that is reasonable and not saturating, it's obviously going to mean that V2 minus V1 is going to have to be very small, right? Assuming I get some reasonable output, not the saturation, right? And obviously we are. I mean, we're not studying this to get saturation, output saturation, positive saturation, negative, right? We're obviously studying this because there is a way to make this V2 minus V1 multiplied by this gain a number that is useful. There is a way to do that, and we will study that. So, but as it is now, if I just plug in a sensor that has any reasonable voltage, and the op-amp output will just saturate to either a positive or a negative value, right? The one nice thing we got with this op-amp is that infinite input impedance issue. So the infinite input impedance is infinite, meaning the current being drawn into this op-amp is 0. The other nice thing we get about the op-amp is that the voltage here at the output of the op-amp will not change regardless of the circuit that you plug here. Will not change. What does this mean? Think of an equivalent circuit, right? If I have my equivalent circuit now of the amplifier looking like this is my amplifier, and the equivalent circuit looks like this. And this is your signal conditioning system after that, for example. This RL is your signal conditioning system that we were playing with in the last chapter. This is A times V input difference, for example, right? Because it's A V2 minus V1. The input difference is the difference between the input terminals. And this is my gain. In this case, it's called the open loop gain, right? A here is called open loop gain. Why is this called open loop gain? Because again, it's a very big number, and we saw that anytime you put a voltage multiplied by this open loop gain, the op-amp will saturate, right? So obviously we're going to come up with a circuit closed loop gain after we add some components that make the circuit useful, right? So when we use it as is, just like that, just in op-amps, and we put some voltages at the terminals, we will get the open loop gain will control my output. This is my V output. The open loop gain is controlling it, right? Anytime I have VID, the output will be controlled purely by the value of the open loop gain multiplied by the input. Even if this is small, this is infinite, it will still be controlled purely by the open loop gain. I do not want that. I would like to figure out a way to go around this phenomena so that I can utilize and build proper amplifiers that multiply my signal by 2 or 3 or 4, something I would like to control. right? So this is the motivation for what we're going to try to do here. So if this is the equivalent circuit of the output, what does this mean? It means I have no resistor here, right? If there's no resistor here, then the V output is equal to A times the gain times the difference between the input, difference between the two inputs multiplied by the gain, right? If I don't have a resistor here. If there is a resistor here, then what is the output voltage equal to? It's the voltage divided between these two resistors. So in that case, if I change RL, will the output voltage change? Yes, right? Because it's a voltage divider. V output is equal to RL over RL plus RS. If I change RL, the output will change, right? Because I have this RS in there. If I don't have RS, then the output will not change. The output will always equal to A times VID, right? So what does this mean for the ideal amplifier? The ideal op-amp, has the output impedance ideally equal to 0, right? So three characteristics of the op-amp now. So R input equal to R input equal to infinity. Our output equal to 0. This is our output. This RS is equal to our output. Yeah, I mean it's the same, right? So RS is equal to our output is equal to 0.
And current entering equals 0.
Huh?
And current entering equals 0.
There is no current coming in because our input is infinity, and there is no change in output voltage because our output or RS here is equal to 0. And the other important characteristic is that the gain is infinite. Open loop gain is infinite. Yes, ma'am. Our input is equal to infinity?
Because no current entering.
But yes, so we don't want, this is the op-amp. This is plus, minus, 2, 1, V2, V1. And the output. This is A VID, where this is VID. So VID is equal to V2 minus V1. Right? So this is A times VID. So the equivalent circuit model is such that I would like to do something useful for me, right? So I built this op-amp, I designed this op-amp, right? Remember in the last chapter we were designing the amplifier and we were selecting values of resistors to make something interesting happen for us. What was interesting to happen for us? What was interesting was that at the input, if I have Vs and the equivalent circuit of the sensor looking like this, that I do not draw any current or minimal current so that I don't have a voltage drop here, so that at my input of my amplifier, I see V input equal to Vs. So what does this mean? I would like Rs to equal to 0. Rs here is our input. No, sorry, Rs is not our input. What is Rs? Rs is the sensor resistance, sensor output resistance, right? But this will have a value. Ideally, I would like it to be 0, but fine. I have a real sensor now, okay? A real sensor, this will not be 0, right? But I still don't want to draw this. So if there's a resistor here, I still don't want to draw current. I'm modeling my signal conditioning system after that as RL. If RL is a certain value, the output voltage here, which is the voltage across RL, which is called V input, that's going into my op-amp. Right, this is the model for my op-amp. This is my sensor, my real sensor. My real sensor has an output resistance. It has some resistance. And then it's going to be connected to my op-amp. My op-amp, how do I like it to behave? I would like it to measure V sensor. I would like V input to equal V sensor as much as possible. I cannot make RS equal 0 just because it's a real sensor. So, but I can design an op-amp. I can select my op-amp or my amplifier. I have control over my amplifier. So I would like to make sure that this is happening. The V input is equal to RL over RL plus RS, right? If this has some value, I would like RL times VS, right? I would like RL to be as big as possible with respect to RS. Ideally, I would like RL to be infinity. RL here is the input impedance of the op-amp. So RL is, you know, R input of the op-amp. Yes, sir.
Why do you want VI to be equal to VS then?
Because the physical phenomena that you're measuring is VS. Light intensity, temperature, flow rate, that's VS. The signal, the sensor is providing you with a voltage corresponding to the physical phenomena, or a current corresponding to the physical phenomena. But the sensor is a real sensor, so it has, it's made of, wires, copper, whatever, conducting materials, and so this conducting material will have an equivalent. This sensor will, producing a voltage corresponding to physical phenomena, but connecting it to the circuit will flow some current. If you flow some current through any material, this will cause some voltage drop. Since it's a conducting material, it will have some conductivity. R equals rho L over A. So anything with a conductivity will have a resistance, right? So RS exists. RS exists.
RS is just the internal resistance.
Yeah, the Thevenin equivalent resistance of the sensor. And this is the physical phenomena you want to measure.
That's the signal that's coming into the op-amp that you're measuring.
That's these are the two terminals coming into the op-amp, right? It's a physical phenomena that you like to measure, plus some internal resistance that you have no control over. This is how the sensor is designed. You have better control over designing your circuit now, because you are given a certain sensor. You want to interface this sensor to your computer system or your embedded system. Your job is to design the amplifier to make it happen, right? So to design the amplifier, I want certain characteristics that are interesting. So because I'm given a sensor that's real, how do I design an amplifier that will deal with this sensor? Ideally, I want my amplifier to reduce this current as much as possible. Ideally, I would like to make it zero. If I make it zero, V input is equal to Vs, which means I'm sensing the voltage at the input. I'm not loading my sensor, right? We're okay with that? So ideally, I would like RL, which is the input impedance of the amplifier, to be infinity. If this is infinity, which is the input impedance of the amplifier, then there's no current flowing here, then V input is equal to Vs, then I'm measuring the physical phenomena. Exactly, or as close as possible, right? So this is the input. And then the output. I have your signal conditioning system is, so now I would like, you have a signal conditioning system that you want this to transfer this to, right? You've taken the sensor data, passed it through your amplifier, amplified the voltage so that it can go into the signal conditioning system with a proper magnitude, for example, or go into your speaker with a good higher current so that you've amplified the power, right? So in either case, you're going to model your signal conditioning system or your speaker as a load that is connected to your amplifier, right? This is going to exist. This RL will exist. You don't have a choice. It will exist, right? So and this will be the output voltage that is going to correspond to the physical phenomena that you measured. So you took V input and you converted it somehow to a V output. Okay, so this is your V output. This V output should be as close as possible to Vs. Fine, your input satisfied that because it took that Vs and made it equal to the V input, multiplied it by some gain A. Okay? Now what? Now, I would like to make sure that my amplifier only takes the V input multiplied by gain A and sends it to the output, regardless of the value of RL. If RL is small, RL is big, I don't care. I want the same V output. I want V output equal to A times V input. Right? I want that to be the same all the time. So, fine. How do I do that? That means first I model my A times V input here as a dependent source. Just taking this input and then multiplying it by a gain, right? What other restriction do I have? Any physical system can be modeled using the Thevenin equivalent circuit. So what's the Thevenin equivalent circuit for my op-amp? My op-amp's output, it will look like this. This is the Thevenin equivalent circuit for my op-amp's output, connected to the load, because current will have to flow, right?
Dependent source.
Yeah, it's a dependent source, yeah.
Still a terminal equivalent.
It's an equivalent circuit. Any physical phenomenon, any voltage source can be modeled as a fine dependent or independent source with a series impedance.
So it's still terminal.
Yeah, any physical phenomenon. Okay? Even power system generators. Power system generator is modeled as a voltage source in series with an impedance. This is what you will use in 338. This is what you use in 459. This is what your power system engineers will use when they go to work. This is equivalent circuit. It's simple. Electrical engineering they only utilize simple equivalent circuits. Yeah. So, okay. So what do I like? What would I like? And this is called my output impedance for my op-amp. What would I like my output impedance to be? If this output, so I would like to make sure that V output is equal to AV input. For that to happen, it means what? That there's no voltage drop across this resistor. Yeah. So if there's no voltage drop across this resistor, I can satisfy it using two ways. Either the current is zero, which doesn't make sense in this case, right? If the current is zero, then I cannot drive my speaker here, right? It's not an amplifier anymore. What's the other option? The other option is to make this zero, right? So our output ideally is zero. That's the other option. So you have to design your amplifier such that your output impedance is approximately zero, and your input impedance is approximately infinity, right? And in both cases, your op-amp is designed with a certain open loop gain A that is very large. Right? We will derive something with a finite gain, finite value for A, but for now, it's a very large number, and that's it. Right?
Is it good that A is a
Large number? It's very nice because it will allow us to do other stuff. Of course, it would be great if I can design op-amps with any gain I would like. It would be great to design an op-amp with gain of 1, 2, 3, 4, 5, 6. But that it becomes ridiculous because you cannot manufacture all of these different kinds of op-amps. But the way that it is now, with an A equals very large gain, allows us to put some circuitry around it to control the closed loop gain. So the A is here the open loop gain, meaning the op-amp operating by itself, nothing around it. Right? Only the input signals V1 and V2, and I measure the output. But if the idea of the property of A being very large will allow us to do something very interesting very shortly, okay? And will allow us to not manufacture millions of op-amps with different gains, because I want to otherwise I would have somebody. Abdulaziz wants to manufacture a gain of 1. You want to manufacture a gain of 2, 3, 4. How many? What's the step of the gain? 0.1, 0.2, 0.01. It doesn't make sense, right? So this would buy us something very interesting next. Yes.
So when you say that this is for an ideal amplifier, and
Yes.
you say, like you said, well, if this is infinity, if this is zero, and A is approaching infinity, then we are measuring the physical phenomenon.
Yeah.
What do you exactly mean by measuring the physical phenomenon?
Meaning your input to the amplifier is equal to Vs. It's not equal to RL over RL plus RS times Vs. It's not a scaled version of V input. So if you're measuring temperature, like if you want to fool me and tell me if you design a poor circuit that is gonna load your sensor, right? Load your sensor means there's current flowing, right? Load means the current flowing, right? If you're gonna load your sensor, right? If RL is infinity, there's no current flowing. That means I'm not loading the sensor. If current is flowing, then I'm loading the sensor, right? If I load the sensor, then what happens? Then I get a V input. That's a scaled version of the sensor data.
So we want Vn over Vs to equal 1.
Instead of V input equals Vs, yeah, or V input equal 1, yes, right? Instead of 50 degrees, you'll be measuring 40 degrees. People can go to work, right?
Okay.
No problem. So you can fool the system by changing the resistor value.
So this makes it basically accurate.
Yeah, of course. You want to, because again, your job is to transfer the physical phenomena, the proper data. You do not want to manipulate the data, right? But you can, if you design a poor circuit, manipulate the data, right? You're loading the sensor in that case. You don't have a proper circuit. You're not really measuring the temperature, right? Okay. So what else? So then the equivalent circuit becomes like this, right? So we have an equivalent circuit for the input that looks like this. Equivalent circuit for the op-amp output that looks like this. This is very similar to what? The voltage amplifier equivalent circuit that we introduced in chapter 1, right? And this is the workhorse of the op-amp's equivalent circuit. We will utilize this equivalent circuit, which is basically an input impedance and an output source, dependent source with a resistance in series, to model the op-amp, right? This is the only one we will use for the op-amp, actually, okay? And what else? We talked about, so this is being the non-inverting input, and this being the inverting input. Why? It's because of the fact that the amplifier amplifies the difference between V2 minus V1. So V1 signal is multiplied by a negative sign. So if you add them together, it's V2 plus negative V1. That's why this is called the non-inverting input, and this is called the inverting input of the amplifier. What's another interesting thing about the amplifier is that it measures V, so the output is equal to A times V2 minus V1, right? That is the interesting thing about that is a characteristic of the amplifier. So if that is the case, and I do something like this, I do something like let's say I do this. This is V1, and this is V2. And then I do something like this, VCM, for example, right? Right? If I do that,
What is the length of OCM?
well, here, for example, let's say VCM is equal to 1 volt. So what is the output equal to?
Do you care whether this is positive or negative? Or
Remember,
none of
this
them?
is V2, this is plus, this is minus. So a good point. So this is V2, this is V1. Again, the output, our equation will not change, right? The output equation is equal to A, V2 minus V1. So what is V2 equal to? It's V2 with respect to ground, right? So V2 is this voltage plus this voltage, right? And V1 is this voltage plus this voltage,
It's negative, negative.
right? So it's V, so it's A. So V2 is equal to what? It's equal to V2. Sorry, I should have called it something else. But it's equal to V2 plus VCM, right? Minus V1 plus VCM, right? So this is equal to A, V2 plus VCM minus V1 minus VCM. So the VCM goes away with the VCM, and I'm left with A V2 minus V1, right? It's not magic. But why is this interesting? Because typically, for example, let's say you have a scope, oscilloscope, or you have any physical phenomena that you're measuring, a flow meter or whatever. Typically, if you have the flow meter sensor inside the equipment that you're measuring, and you bring the wires all the way to your signal conditioning system or your computer or whatever, right? Again, this is a piece of wire with a potential, charge on top of the wire, another wire with another charge. If you have two wires with charges, a wire with with charge across it, what will that do? If you have a piece of wire from 322, if you have a piece of wire with charge Q deposited on top of it, right? What is that going to do? It's going to cause an electric field around. Electric field that is radially emanating outward. This electric field will do what? Inside this electric field, between any 2 points in the electric field, right? Between this point and this point, there's an electric field. This electric field has a gradient, right? The farther away you go from the charged particle, the lower the electric field is, right? So there is a gradient to the electric field, and the electric field units are in volts per meter. So it starts with a value and then goes to another value. What does that mean? It means between any 2 points in space that has an electric field, there is a voltage difference, right? There is a voltage, 1 meter away, equal to the electric field strength. 2 meters away equal to the electric field strength divided by 2, for example. Right? It's the electric field strength is in volts per meter. So every meter, if I measure voltage with respect to ground, it will be some value. Right? So there, that means that any 2 points in space around the conductor will have a voltage across them. Right? You agree? From, I think, 322, right? This is
We
322.
didn't study it.
Electromagnetics, you didn't take
One second, next semester.
taking it now. Okay.
I'm not taking it.
But Ahmed took it, right? So you took it, so you're taking it now? So you study this now or not yet? Okay.
We
But,
didn't study
Next semester.
okay, so you will study this at some point. But what I'm trying to say is that anytime you have current flowing in a conductor, or meaning charge deposited on the surface of a conductor, it will cause a voltage difference. A voltage difference between any 2 points in space around it. Okay. Now let's say you put another conductor at that point in space. What does that mean? That conductor is within that electric field. It will have a voltage difference between it and the other conductor. There will be a voltage difference between them because of the electric field that you've placed this conductor in. Okay? So now let's say you have this sensor measurement, flow meter measurement system with 2 wires coming out. Right? You don't know what's around. Right? So sometimes you will measure something that will be weird, something with noise, for example, or something with an offset, and you will be confused what's going on, right? So some signal has coupled to the wire due to magnetic field or electric field. Okay? So some electric field will do something, magnetic field will do something, right? So some signal has coupled to the wire. This signal has coupled, both wires are moving together. If you made one wire doing this and one wire doing that, not identical or very different from each other, away from each other, then this external signal may couple to them differently. But let's say you did your job as an electrical engineer and made sure that you brought the wires together and you twisted them, for example, all the way to the signal, so they sort of are seeing the same effect, right? Especially after you twist them, then every point on the wire will probably see the same effect. So this external signal that's coupling, it's called the common mode. We can model it as a voltage. We will call it common mode voltage. Common mode voltage. So it's an external signal that couples to the wires, to the inputs of the amplifier just because you have wires coming through, or if you made a board, an electronic board that has a switching power supply, high voltage switching power supply next to a sensor, for example, and they're affecting each other. It's causing some magnetic and electric fields that are affecting the inputs, or that are causing a voltage at the input of the op-amp, for example. Right? Whatever it is, right? It's a common mode voltage. We want to eliminate common mode voltages because they're not our signal. Our signal is V1 and V2, right? Our sensor is giving me V1 and V2. This is my input from my sensor. That's what I would like to measure. So the nice thing about the op-amp is that it ideally can eliminate common mode voltages. Ideally. And why I say ideally? Because we will analyze this in more detail later in the chapter, right? But ideally speaking, I can eliminate common mode voltages. Excellent. Any external noise that couples to this thing, I can eliminate it easily. So that's a nice characteristic that, for an ideal op-amp. So one of the important measures that we will utilize for an op-amp is its ability to eliminate this common mode voltage. And we will call that CMRR, common mode rejection ratio. And we will plot that in dB as well. So it's called common mode rejection ratio. Right, CMRR. And that we will define later as, what do you think this will be defined as? It will be defined as, the gain of our circuit for the differential input, V1 minus V2, differential input is V1 minus V2, over the gain of the circuit to the common mode input. Right? There is some common mode signal that we drew before. If this common mode signal passes through with a gain, that means I'm amplifying the common mode signal. So this is this one. Versus what I would like is I would like to only amplify the differential signal. So this is the V common mode is my common mode signal. I would like to amplify this, and I want to reject this, right? So common mode rejection ratio is the ratio between what I want and what I don't want. I would like this to be as high as possible, right? Or reject as much of that as possible. And of course, you can plot that in dB as 20 log, AD over A common mode, right? Differential gain over the common mode gain. Okay.
So
Yes.
you want ACM to be 0 or VCM to be 0?
I would like VCM to be 0. Common mode. I would like the common mode voltage to be 0,
What about
but
ACM?
it's not. It's not V0. I mean, VCM is not going to be 0, right? So ACM is going to exist. We will see why. Later we will derive the common mode gain, right? But for now, fine. If this signal passes through and it's amplified, that means that there's a common mode gain. Somehow we have to derive this common. We talked about the differential gain. Differential gain is open loop differential gain is A. This is the open loop differential gain. This is A. What happens to the common mode signal? We will look at it later in the chapter. Yeah. Other terminology that they utilize in the textbook, they also use, we also, we call these, the fact that the op-amp has two inputs, we call this differential input. Differential input. And we have one output with respect to ground, so we call this single-ended output. That's another term that they utilize in the textbook. And as we said, the ideal op-amp responds to the differential input, and it rejects the common mode input, right? Common mode input is the input that is common to both terminals, right? It's like I have 1 volt placed across on both terminals. So if I just do this, and I have VCM here, what do I get at the output? 0, right? Ideal amplifier will have a common mode. The response to the common mode will be 0. That's the ideal amplifier. Okay, what else? We said we also later. I mean, so we talked about the DC coupled amplifiers, right? We said DC coupled amplifiers are ones that do not attenuate the signal at DC. So this is a DC coupled amplifier versus this is a capacitor coupled amplifier. This is an indication of that. Op-amps, we said, are DC coupled amplifiers. Is this good or bad? Again, later in the chapter we will see that this causes some limitations. So, but this is just a fact of life. We will have to live with the fact that these are DC coupled amplifiers because these are typically on integrated circuits. And we said that for proper capacitor coupling, you would need to have a large capacitor to be able to do this capacitor coupling and attenuate the signal. Right? We discussed that last time. These are integrated circuits. Op-amps are built on integrated circuits. You do not have the luxury or the real estate on the chip, on the chip to build a large capacitor. So that's why it's a DC coupled amplifier. And as we said, it has infinite bandwidth. So infinite bandwidth, infinite gain, input impedance equal to infinity, output impedance equal to 0. So all these are interesting characteristics of the op-amp. So they're summarized here in the text. So this is a summary of what we talked about today, right? So it has infinite input impedance, 0 output impedance, 0 common mode gain, right? The common mode just signal disappeared for an ideal op-amp, or equivalently infinite common mode rejection. So it's either the common mode gain is 0, or which means that I'm infinitely able to reject common mode signal. And then it has an infinite open loop gain, and it has an infinite bandwidth. So this is the summary of everything we talked about. Does everybody not see where this is coming from on the three terminal device? Can everybody explain or understand basically how these points summarize everything we talked about? You're okay? Anybody not understand one of these points and how they relate to what we talked about? Raise your hand, please. We're okay? Okay. Yes.
So we have infinite input impedance, so we have current equals zero.
Yes.
And we have zero output impedance, so we don't mess with the,
The voltage in the output does never change.
so we don't mess with this, with whatever signal we're, like the physical phenomenon that we have, right? So
Sure.
we don't get anything extra, as
Sure.
you said.
No changes in, again, you don't get changes in the output voltage due to any changes in the load that is connected
And
to.
zero common mode gain, so basically this is when you, as you said, the wires, so we don't have difference.
If you have any signal coupling both terminals, for example, due to electromagnetic interference, due to electric field, whatever,
What about the last two?
the last two, infinite open loop gain, that's what we were talking about from, it's a physical characteristic of the op-amp, the fact that the output is equal to A times V2 minus V1. This is actually why we cannot use the op-amp unless we are by itself, except if we're using it as a comparator. This is a good and a bad. Okay, it's a good and a bad. It's good if you're using it as a comparator, but bad if you're using it as an amplifier, because there is no way to control what the output signal is going to look like. This is V output. So if this is infinity, what is V output? Regardless of V2 and V1,
Whatever
it
the
doesn't
power.
make sense, right? So this is why we're going to go to and build the inverting amplifier. So put circuits around it. This is the reason, the motivation why we need to put circuits around it. Put resistors and capacitors around it, yeah. And we will see that when we start putting resistors and capacitors around it, we're going to be messing with other stuff. Okay, you put the resistor at the front. What does this mean? It means you're going to be modifying the input impedance. Luckily, we don't have any circuits that are going to be putting resistors at the output. So, good thing is we're not going to be messing with the output impedance. But most of the circuits will be messing with the input impedance. Is that good or bad? We know that if we bring the input impedance low, it's bad. If we're trying to amplify the signal, right? If we are just trying to create a unity buffer, maybe not a big deal, right? We'll see that in more detail. But a lot of the circuits are going to be messing with this. And then we will see that, ideal, yes, common mode rejection is for an ideal op-amp. But real op-amps, they actually do allow the common mode signal to be amplified. And we will see how to control that so that you don't get something at the output that doesn't make too much noise or nonsense here. And then infinite bandwidth, that's just, that's a fictitious thing. Everything has a limit. Every physical phenomena has, or every physical system will have a limit on its ability to pass signals with different frequencies through. Okay, so but this is the main motivation for what we're going to talk about next. So what do we talk about next? So we talked about the differential signals. So these are just some definitions again based on the discussion that we just had. The VID is the differential input voltage. It's the V2 minus V1, the non-inverting minus the inverting output voltage.
Differential input out. What?
Differential input signal. A differential input signal, right? So we have a signal at the input, V2 minus V1 plus minus, this is 2, 1. So this signal here is called VID. It is called the differential input signal. This differential input signal VID is equal to V2 minus V1, right? If we have a common mode signal, right? Common mode signal means a signal connected to both, that is affecting both terminals the same way. So what is the value of that? So if I have 1 volt common mode voltage here and 1 volt common mode voltage here, 1 volt, 1 volt, right? You know that this common mode voltage is 1 volt, right? So what is this common mode voltage equal to? This common mode voltage is equal to the voltage at terminal 2 plus the voltage at terminal 1 divided by 2. So if I put 1 here plus 1, that's equal to 2. 2 divided by 2 is then my common mode voltage is equal to 1 volt, right? It's 1 plus 1, 2. 2 divided by 2 is 1, right? So yes, I had a common mode voltage of 1. This was my common mode voltage that I added to the circuit here. Okay? So then of course I can draw an equivalent circuit like we did before, where I have a relationship between the input voltages and my common mode voltage. So I can solve for V1, for example, and utilize it here. If I solve for V1 and put it here, then at each terminal, right, I have some common mode and some differential signal. Some common mode and some differential signal.
Like an imaginary embryo.
Like an imaginary, if you want to call it that, but it's not, fine, it can be a complex number or it cannot, But basically what I did was solve for V1 and substitute here. Or solve for V2 and substitute here. Right? If I solve for V1 substitute here, then I have a relationship between V common mode and V2 and VID. If I solve for V2, right, and substitute here, then I have a relationship between V common mode, VD, and V1. That's what I have here. Okay. We'll stop here. We'll continue next time.
Can we turn in the homework and
Yeah, the homework's to be returned in class, so you should be giving me the homework. Yeah.